names. Now we can use chemical equations to represent reactions. And to make things even easier, we can actually use models to represent these chemical reactions. Traditionally, in a chemical reaction, chemical substances actually break apart, and later on they will rejoin again together in a specific manner to form new compounds. Now, there are two sides of a chemical reaction. On the one side, traditionally on the left side of the arrow, the chemical substances that are reacting together are called reactants. While on the right side, or on the other side of the arrow, the new substances that will then be formed after the first ones have reacted, the new substances, the resultant substances that will be formed, are called products. So we could then use models to represent the atoms of the different elements, just like we saw with the model of water earlier, where we had the white atoms that represent hydrogen and the red one that represents oxygen. So we can then use this model to completely represent a whole chemical reaction where we have in just models. And why do we use that? We use it so that it can make it easy to understand the manner in which these reactants break apart and the manner in which they will then rejoin in different ways to form the products that they are supposed to form. Conversely, and actually most conveniently, we can use symbols and formulae to represent reactions. It's not easy to always draw out models. It's time-consuming and requires a lot of artistic work. But with symbols, we can write them out as if you're writing just words. So it's much more easier and much convenient and faster. So you then will be required to use your knowledge about these symbols. We've done that in the periodic table, and the formulae to represent these chemical reactions. And that chemical reaction that is fully represented, like this one here, is what we refer to as a chemical equation. And like I was saying earlier, there are two sides to it. There is the left side, where we have the reactants. My reactants here are hydrogen and oxygen. And the right side, where we have the product. My product is a compound formed from those reactants. My product is water, or dihydrogen monoxide, like we saw earlier. Now, this is the example of water reacting with oxygen to form, or the example of hydrogen reacting with oxygen to form water. And the equation is written as follows. Oxygen on the one side and hydrogen on the other. If we look at this equation, if you look at the different molecules that are involved there, we will notice there are subscript numbers in each of the formulae. It's a subscript number here. They are represented in green. In each of the formulae or symbols, there are subscript numbers. And these subscript numbers indicate the number of atoms. Please don't confuse. We are looking at the number of atoms and not the number of molecules. There could be several atoms in just one molecule. That's what it means. There can never be molecules in atoms. Okay. Could be several atoms in one molecule of an element or in one molecule of a compound. So the subscript numbers indicate the number of atoms in either the element or actually the compound. So we have two hydrogen atoms in the molecules of hydrogen that's formed here in the molecule of hydrogen here. We have two oxygen atoms in the one molecule of oxygen that we have here. We have two hydrogen atoms and one oxygen atom in the molecule of water that we have here. And again, there are other figures that are indicated here, other numbers that are also indicated here in red this time. In red this time, we have numbers that are found in front of the formula, or just some of them, and they are shown in red. These numbers indicate the ratio in which the molecules react, or they also indicate the number of molecules represented in this chemical equation. Now, for example, I have 2 here in front of hydrogen. It tells me that we have 2 molecules of hydrogen. Here I have nothing. It means there is a silent 1 somewhere here. It tells me that there is just one molecule of oxygen to react with 2 molecules of hydrogen, and also I have them 2 molecules of water that will then be formed. Diatomic elements. Di means 2. And what 2 are we referring to? These are elements that if we look at each of their molecules, we will realize that for every molecule, there will be 2 atoms that are present in each molecule, just like we have here. This is a molecule of oxygen. If we look at this molecule, you will notice that there are 2 atoms of oxygen. It means to form one molecule of oxygen, we need 2 atoms of oxygen. For some other elements, to form one molecule of that element, we'll just need 1 atom of that element. That's what it means. So there are cases here where to form a particular molecule, 2 atoms of that element will be required to make that molecule. Now, we use oxygen and hydrogen gas in chemical reactions very often, but in nature, the atoms of these elements, oxygen and hydrogen, always react in pairs of 2 because their molecules are made up of 2 atoms. So it's very normal that each time that they will have to react, or if each time that will be found naturally, they'll be found with 2 atoms in their molecules, and so goes as well with their manner of reacting. Now this is a list of elements that have 2 atoms in each of their molecules. We have, for example, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They have 2 atoms in each of their molecules. They are diatomic. So each time that we use them in a reaction, and if in that reaction they are used as part of reactants, we must always use them, always adding the subscript 2 that we see everywhere, as long as they are not part of a compound. So if they are part of the reactants, for example, those reactants that we found on the left side as pure substances, if they are part of just reactants, we'll always write them out with a subscript of 2. If you saw the previous reaction with hydrogen and oxygen to form water, on the left side, hydrogen had a subscript of 2, that was in green. On the right, and oxygen also had a subscript of 2 that was in green. But then in the compound side, the product side, when we wrote hydrogen, it had a subscript of 2, and oxygen had a subscript of 1, which was silent. It was not represented there. So in their free form, we'll always write them as they're supposed to be with this 2, 2, 2, except when they form compounds, when they could have different subscripts. They could have 2, they could have 1, they could have 3 or 4. Change depending on how many atoms of them were used in making one molecule of that compound. During a chemical reaction, atoms are conserved. Atoms are not lost or gained during a chemical reaction. This stems down from the saying that matter is neither created nor destroyed, but just changes from one form to another form. That's all that happens. We don't create, we don't destroy, we just modify. That's the same thing that happens during a chemical reaction. Atoms are not lost or they are not added, they are not gained. It means that the original atoms that are found in the reactants simply rearrange themselves to form new groups of atoms in the products. There's just a rearrangement. There's nothing that is subtracted, there's nothing that is added. Even in other chemical reactions where we see, for example, one atom will be lost. For example, if I had 2 hydrogen plus 2 oxygen, it will give me simply H2O. It looks as if in this case here, in this molecule, we've lost 1 oxygen atom. It doesn't mean it is lost. It's still reacting. It's still going on with other atoms of hydrogen to reacting to form more molecules of water. And still at the end of the day, the accumulated oxygen that will be formed from all the 1 that was lost in each of these atoms, that oxygen will remain in the form of oxygen and will still be present. So it's not lost. So then, when we look at our first equation here, the models, this is the use of models, like we said earlier, to represent a chemical reaction. In this model, I have 1 atom of carbon. Carbon is monoatomic. You see here, it's only 1 atom per molecule. While oxygen is always diatomic. You see 2 atoms of oxygen, like we said earlier, is diatomic. So in this reaction, I have 1 atom of carbon reacting with 2 atoms of oxygen. And what do we have at the end of the day? We still have 1 atom of carbon, just like at first, and 2 atoms of oxygen, just like we had before, to give us carbon dioxide. The same goes here in the formation of carbonic acid. We have 1 molecule of water. This time I'm looking at molecules. 1 molecule of water, and we have 1 molecule of carbon dioxide here. They are reacting to form carbonic acid. But when we look at those molecules, what do we notice? Here we have, in the molecule of water, we have 1 atom of oxygen and 2 atoms of hydrogen. So let's keep in mind, we have 1 oxygen here and 2 hydrogen present here. And on the other side, with carbon dioxide molecule, we have 2 atoms of oxygen. So on this side already, I'm no longer with 1 oxygen atom. I'm already with 1 plus 2. That should give me 3 atoms of oxygen and 1 atom of carbon. So this side here comes with 3 atoms of oxygen, 2 atoms of hydrogen, and 1 atom of carbon. Let's look at carbonic acid on the other side here to see what we have. With carbonic acid, we have here 1, 2, 3 atoms of oxygen, 1, 2 atoms of hydrogen, and 1 atom of carbon. I'm sure if you look at it now, we will see that 3 atoms of oxygen balances with 3 atoms of oxygen on the left side. We see also 2 atoms of hydrogen balances with 2 atoms of hydrogen on the left side. And we see also 1 atom of carbon balancing with 1 atom of carbon on the left side. So we can clearly see, like we said, that during the chemical reactions, atoms are not lost or gained. They are simply rearranged, because the arrangement here is different from the arrangement that we had here. Now, in order to account, like I said earlier, when we have 2 of hydrogen combining with oxygen, 2 here, and we're having H2O, in order to account for the atom of oxygen that is lost here, we'll have to then work out what we call balancing of chemical reactions, or balancing of chemical